Now, the previous video was getting a bit long. I was going to include a summary of what I did to read the PAL chips going these two sockets here, but it was an interesting exercise, and I thought maybe it should have its own video, and that's what I've decided to do, and it makes the other video shorter. So this is what happened. Here, the two PAL chips that live there, I plugged into this contraption, which is the little board I used when I was fixing my PDP-11 console. I call it the tester or exerciser. It's just an Arduino Nano with all of its outputs going via, I think, 100 ohm resistors to these pins along here, and then I connect those into this breadboard where I have a ZIF socket for putting in the PAL chips, and then plug that into a PC. And the software inside the Nano is very basic. It just receives commands from PC that tells it to write data to the three ports, port B, C and D in the AVR chip, out to these lines, and then that goes into the chip. So, and then read some of them back and send it back to the PC. So it just does what it's told. It doesn't do any thinking. So the reason I made this video is because I originally thought reading out the contents of this PAL and Arduino would be fairly easy. Just connect it up like I've got here and throw bits at the input pins and read the output pins, and there you go, which is perfectly possible, but the results would not be very meaningful. I'll try and show why that is. First, let's just have a quick look at the chips involved. Here's a data sheet for the chips. It's a 20 pin family of chips, which basically has a bunch of inputs going into an array of AND gates, rows and columns. I'll show that on the next page, and then from that inputs go into OR gates. In the case of these chips, they're NOR gates. So looking at one of them, the PAL 12L6, he has 9, 10, 11, 12 inputs and 1, 2, 3, 4, 5, 6 outputs, plus power and ground. So you can see each input is converted to both its true and complement form by an inverter, and they go into these columns, and then rows across the columns go into these NOR gates, and there's a fusible link at every intersection, and the programming process burns out the fusible link. So these are TTL devices, not CMOS, so they're not likely to have been damaged by static discharge, and they're not like an EEPROM, which relies on a bunch of electrons staying in a little insulating well and not escaping. These are pretty hard and fast solid connections. They're either there or they've been burnt out. So the chances are these chips don't lose their contents, but it's still worth recording what's in them. The other chip is a PAL 10L8, and he has 9 inputs plus another one, 10 inputs, and 1, 2, 3, 4, 5, 6, 7, 8 outputs. Again, with the inputs being inverted and non-inverted into columns with links that allow those columns to connect to these NOR gates. Now you might notice that one of the issues, which we'll get to, is how it's a bit of a dog's breakfast in there. Like that first pin doesn't go to the first column, nor does the one around here. It's the second pin goes to the first column, and then the pin 1 goes to the second column, this goes to the third, 4th, 5th, 6th, 7th, 8th, then this one goes to the 9th, then the 10th, then the 11th. It's all over the place. That's just one of the problems, but that's illustrative of the whole issue involved. And the problem is mapping. Inside the AVR there are 3 ports, port B, C and D, which are, that's an issue because I'm writing directly to the ports. If I use digital write and digital read, I'd just be dealing with the nano pins, but because I'm dealing directly with the ports, there's a mapping there, and that mapping is shown in this diagram. The port pins, port bits, PD, PB, PC, they map onto particular Arduino Nano pins according to these numbers. So there's a mapping from those to those. That's the first level. Then within this board we've got another mapping which is from which nano pin goes to which of these pins. So here's my PCB layout. The nano pins go to through 100 ohm resistors to these pins along here. So that's a second mapping. Then we've got a third mapping, which is which of those pins go to which pins on the PAL chip. And I suppose we've got a fourth mapping, which is which pin goes to which output. But yeah, that's the mapping we're trying to uncover, so it doesn't really count as a problem. And then finally, when that chip is inside the Uniboard circuit, we've got another mapping, which is which pin on the PALs, there's one of them and here's the other one, which pin on those goes to what signal on the Uniboard. And you can see also, this is a dog's breakfast as well, like the address lines, A4, 5, 6, 7, 8, 9, 10, 11, 12, they're in order, but the pin numbers that they go to on the PAL are all over the place. So that's a fourth, or if you like, fifth mapping. Here at least there's some order to the inputs, they're the address lines, but on this guy they're just a whole bunch of different signals with no apparent relation between them, or certainly no ordering to them. The outputs have a bit of order, they're the CAS signals, so there's some order there, but not on the inputs. So if you were to just write output bits to this thing and from the Arduino to the inputs on this thing, read its outputs, what would you do with the results? It'd be very hard to interpret what they meant. I'll show you how I've dealt with that. One other thing, these PAL chips, luckily they are just this simple form of inputs going directly to outputs. So the outputs always depend only on what the inputs are. There's another variety of these things which are called registered, and they have a bunch of flip-flops in here, so that the output you get from it depends not only on the current input but also on previous inputs that have set the states of those flip-flops. And that would have been probably a nightmare. I don't know if that would have been possible to extract the data from, but fortunately they're a simple type. We can just treat them basically as a read-only memory. Apply inputs as addresses and read out outputs as data. So I'll show you my software that I wrote on the PC that talks to this, and see how I dealt with the mappings. So in my code I have an array, pinrecs, an array of total pins, which is 20, of tpinrec, which is a record of with all this stuff in it, which contains all the information I need to know about any pin. And then part of the initialization is it runs this procedure, which sets up the relationship between the AVR port bit, so PB0 through 5, PC0 through 5, PD2 through 7, relates them to which of the pins on the Arduino they go to, and then which pin they go to on the exerciser. So we're mapping from the AVR to these pins, and then from those pins to these pins, and that defines this thing. Then we've got a procedure for each of the two different PALs. So the one for the 12L6, we say, and this here is the name of this pin along here, so that's the key that joins the two together. Those names are these names. So that relates from an AVR port bit to one of the pins on the exerciser board, and then the exerciser board relates to pins on the PAL chip, whether it's an input or an output, a name. Now these pins don't have names, so yeah, what do you call them? And I just dreamt up these names based on what they connect to internally, but I don't use them anywhere, so they're pretty meaningless. The next mapping is to what they do on the Uniboard. So these are the actual signals on the Uniboard. And for the other chip, likewise, we relate the pin number on the exerciser to the pin on the chip, whether it's an input or an output, some internal bullshit name, and how it's used on the Uniboard. This last column, I'll show you where that comes in. If we look at how these things are used on the Uniboard, we're looking at the first chip we looked at was this one, the 12L6. The inputs on that are the address lines 4 through 15. So the other, and this is the other issue to do with these things, what order do you set the bits going into these chips to read them out so that the results you get have some meaning? Well, for this it's fairly straightforward. They're just address lines, so they're just a number. What is it, a 12-bit number, so you just increment them starting off at all 0 until they're all 1s. And this one, being the lowest one, will toggle the most frequently, and then this one every second time, and this one will only toggle twice during the run. Sorry, A15. But notice it doesn't start at A0, it starts at A4, so the bottom 4 bits of the address don't go into this. So it makes sense to, rather than treat the first code being all zeros, so let's go to the second address. When we turn on A4, rather than that being address 1, because that's the lowest order bit, it really is address 0010. So we should treat the values we stick in there as the addresses on the Uniboard system, not just the addresses going into the PAL, and take account of those 4 bits that don't go into here. And that's why A4 there has a value 0010. So, and then the next one up, A5, 20, A6, 40, A7, 80, through to A15, which is 8000. So the low order nibble is always 0, but we include it so that when we dump out the results, they'll be in proper address order as per what's going on inside the Uniboard. For the second chip, there's the pins aren't related together that well. There's no actual order to them, but I've given them a value anyway, just so that I can hopefully extract some order, some sense from them, but this is a bit arbitrary. So that's what we get. That's how I've dealt with this mapping and deciding what order to present the inputs to the PAL, so that when we dump out the results, they're in some sort of order that makes sense. Now in the main line of the code, I've got this reset pin data. That's that first procedure this gets called out of reset pins data. Then we call either set up PAL chip U32 or 40, which are those other 2 procedures. We want 32 because we're going to deal with this PAL 12L6, so just made sure that is what we've compiled with. I can't compile on this machine because I haven't got everything needed. So I compiled it on my desktop and brought it back here after making sure that it's for U32, not U40. So let's close that and run the executable. So there it is, all plugged in, connected to the USB. Okay, we'll run the general tester controller. There it is. Find out what port the thing's on. COM4. So now we just run it. And it's going through sending out all the increasing address values to the input pins and reading back what the outputs have. And there's 12 inputs, so there's 4096 combinations of inputs. And there we go, all done. I didn't notice when I ran that test on this chip that it was actually reading back all 1s all the time. So this is from a previous run. I don't care why it didn't work then, because I've got the information in this file here. So describing it, it first puts out a heading just to say which chip it's working for, the PAL 12L6, which is U32 on the Uniboard, and then a sort of a dictionary legend to describe what follows. Here we have it's sequenced in order of the PAL pin number from 1 to 19, and we'll see that pin 10 isn't included because that's a ground. Whether it's an input or an output, the arbitrary value that was assigned to it, and the signal name on the Uniboard, so to give it some meaning, this rather meaningless internal name of the PAL pin, because the PAL chip doesn't have any actual pin names. This is the pin number on the exerciser tester board thingy, and this is the bit number inside the AVR, PC 0 through 5, PB 0 through 5 and PD 2 through 7. Then it compiles all that information and produces this bit mask that says this is what has to be sent to the AVR for ports B, C and D to activate that particular signal. So for instance, A4, to turn on the A4 signal, which is actually pin 7 on the PAL, but address 4 in the Uniboard, we have to send 04 0000 to ports B, C and D. Okay, so that's just a bit of documentation. Then we have the actual output of the run, where we show the stimulus we're sending to it, which is just an increasing from 0 to 4095, both in decimal and in hex. This is the value we send to ports B, C and D for each of those different stimulus values. And this is the result we read back from ports B, C and D. Then we clean it up, mask off what we don't want, and present it this way as PAL pin numbers from 1 to 20. 20 of course is always a dot because it's the power pin, and likewise for pin 10, which is always a dot because it's the ground. These others are the inputs, plus that one up there, so you can see they're going through various values. And then the output pins are pins 13 through 18. They're in a block together. Then we show the inputs to this thing are the address bus, but it doesn't turn on the low order nibble. It's always 0, 1 in the second nibble, because it's effectively shifted across 4 bits, because A4 is the lowest one going into that chip. And then here's what we read back, which is always just that's as high as you get, 3F, because it's only 6 bits. And you can see that's often 3F, but if we go along further, we occasionally get other values. And finally we're done down here, 4095 combinations read out. Then I'm attempting to try and make some sense of that. And we have, for each of the output pins, pin 13 on the PAL, the arbitrary value we assign to it, how it's used on the Uniboard. So this is chip select for the 6844, the DMA controller, and we can see its output is always 1, except just there. Now this is a bit of an old run. I think I've got another run where this is where the 1s, because that's pretty much the default, is a dot. So I'll find that, I think. Yeah, this is better. Because those outputs on the PAL chip are NOR gates, they're active low because the output's got an inverter on it. When the output is high, I just put a dot there, so it's easy to see when we get a 0, which is low, and there we go. And that happens at address EC, ED, EE, EF 10 and 20. EF 10 and 20. And if we look at the Uniboard memory map, the DMA controller is EF00 to EF1F. So it takes 32 addresses. So each one of these dots, of course, is 16 addresses, because the low order bit is not, we're not changing the low order nibble. So yeah, EF00 through to EF1F is the DMA controller. For instance, the monitor ROM lives at the last 8K, is it, of memory? I think it's the last 8K, maybe it's 4K. From EE00 to EEFF. And so we're looking for chip select of the 2732. There we go. So it's always high except that last 8K or 4K. I can't be bothered trying to work out which it is off the top of my head. But yeah, that's the end of memory. That's where the ROM lives. So its chip select goes on then, and so on for a few other chips. So it seems that all those outputs do match up with this memory map. So I'm happy that that chip is got valid contents in it. And if we were to look at the other one, PAL 10L8, the U40, which has less meaningful inputs, they're certainly not in any order, so they're applied to the thing in the order that I've dictated by the value given to the pins, but it's pretty arbitrary. If we go down to the results coming out of it, this is a bit harder to interpret because we're not sure what all the pins actually mean. I mean, okay, CAS, we know what that is, that's the column address strobe for the RAM, and it seems to make, it looks like it's sort of sensible, so I'm pretty sure that's right too. But yeah, I wanted to interpret this stuff a bit better, and I actually posted a query on the EEV blog forum asking if anyone knew of an algorithm that would help sort this stuff out, and there was a couple of suggestions that pointed me on a line of research that took me to a thing called Logic Friday, where I could, this information, the raw binary input and output, and reformatted it into a simple text file that could be inputted to this program Logic Friday, and it produced this. There's the truth table data that was input, and it generated that, which is rather meaningless, but you can then tell it to produce a schematic of logic gates that would produce this truth table, and that's what you get. So I can see now that all the outputs depend on all the inputs in some way, so that there's not as if there was two distinct blocks of inputs to one set of outputs and an independent distinct group with other inputs going to other outputs. They're all interrelated, and you can, now that's telling it to use no, that's what it defaults to, using inverters, NOR gates and AND gates, but you can tell it to use a whole bunch of different things, including multiplexers, or gates, or NOR gates, AND gates with multiple inputs, whatever. So presumably that's the simplest possible logic diagram. Or you can tell it to use NANDs only, or NORs only, and this is how you'd get it with that. Yeah, so that should be helpful to debug it, and you can also edit this thing to try and rearrange it to make a bit more sense. Yeah, so a very useful little tool. It's called Logic Friday. That's what I did to read the PALs. I'm fairly confident that they're intact, that they do have the right information in them, because it seems to make sense, at least for one of them, and they should be pretty robust devices anyway, being TTL and tungsten fuses that are unlikely to burn out just by themselves. Yeah, I hope you found that interesting. This Uniboard saga will continue, so for now, catch you later.